Alright guys, we're going to finish off the momentum unit with an idea called impulse. So impulse and the change in momentum are directly related. Recall that Newton's second law states that F net equals mass times acceleration. So we're going back in time a whole unit. But also remember the equation for acceleration. Acceleration is Vf minus Vi over t. We can combine these two equations. So F net equals mass, and I'm going to plug in this entire value for acceleration. Vf minus Vi over t. Now I'm going to do two things. The first thing, I don't like fractions, so I'm going to multiply both sides by t, and these two cancel out, and I have F times t equals m times Vf minus Vi. Now this is a pretty useful equation, so this is one that you want to make sure that you have written down in your notes. But in addition to show you this relationship, I'm going to do one more step. So F times t, I'm going to distribute that m, equals mVf minus mVi. Okay, so there are two important things here. F times t, this entire side of this equation, this is impulse. There is no symbol. F times t is impulse. It's not I, it's just force times time. This side of the equation, mass times the final velocity minus mass times the initial velocity, is our change in momentum. So based on this substitution in this equation, impulse is equal to the change in momentum. F times t equals mass times final velocity minus mass times initial velocity. So the quantity F times t is called impulse. It's the product of the force applied to an object over a given time. Both the amount of force as well as how long it impacts the object affects the motion. Impulse is measured in newtons times seconds. We know that if an object has mass, it's moving, and it has momentum. Objects with a higher momentum are harder to stop from moving. To stop an object, we need to apply a force over a period of time. A higher momentum means that you need a larger force or a larger amount of time for the force to be used. Impulse can speed an object up, slow it down, or completely change the direction of the force. In class, I'm going to show you a couple of videos that directly relate to this slide. We are going to see a video of how a bullet can change somebody's path of flight and whether it's believable or not believable or scientifically supported or not. We're going to see a video about using body weight to stop a moving vehicle and if it's plausible, or what other options you may have using the same body weight but maybe changing the other characteristics. So we're going to see some video examples of these in class. But here are some examples that I don't need to show you videos for. If you participate in an egg toss, and most people have done this on field day or at summer camp, when you stand 2 feet away from somebody and you have to toss the egg and they have to catch it without it breaking. And if you do that the first time, each of you takes a step back and you do it all over again. Well, eventually when you are a lot of paces apart, you have to toss that egg with a high initial velocity. But then you want to make the egg stop on the other side as someone catches it. So instead of stopping it and catching it fast like a baseball, you cradle your hands, catch the egg, and then move your hands backwards to slow it down over a longer period of time. That is increasing the amount of time so you can use a smaller force to stop the egg. Airbags in a car are another example. If you come to an abrupt stop, your body wants to continue moving forward. So the airbags in the car deploy and create kind of a pillow for you. They deploy and then slowly deflate to make your head come to a complete stop. The last one is hitting a ball completely versus bunting a ball. If you've ever played baseball, you know that there are some situations where it's better to bunt the ball instead of trying to hit it all the way through. When you do this, you do not allow the bat to swing fully through its arc of motion. So instead, you stop the bat very quickly, the ball bounces off the bat and travels a short distance in front of the batter. If you were to swing through, the bat would actually be in contact with the ball for a longer period of time because it is stopping the ball from moving and then pushing it in the opposite. So hitting the ball with a bat, you have a larger force and a larger amount of time. That's why the ball travels farther. Bunting, you have a smaller force and smaller amount of time. That's why the ball doesn't travel very far at all. So here's a practice problem. A force of 4 newtons is applied to a ball for 0.75 seconds. What is the impulse? Now, we don't have a symbol for impulse, but we do know that impulse is equal to force times time. So the impulse of that scenario is the force of 4 newtons times 0.75 seconds. So our impulse is 3 newtons times seconds. A driver accelerates a 240 kilogram snowmobile from 6 meters per second to 28 meters per second. What is the impulse that the snowmobile experiences? So I'm going to go back to the equation from the previous slides. F times t equals mass times Vf minus Vi. F times t is my impulse. So I don't need to use any information to solve for that because F times t is, by definition, the impulse. So I have 240 times 28, because that's my final velocity, minus 6. Impulse equals 240 times 22, and my impulse is 5,280 newtons times seconds. Last one. A 0.105 kilogram hockey puck is traveling 12 meters per second when it's struck by a stick. As a result, the puck travels at 15 meters per second in the opposite direction. If the contact between the stick and the puck lasted 0.05 seconds, what is the force? So I'm going to go back to that original equation. F times t equals m times Vf minus Vi. But over here I'm going to list my knowns and unknowns because one part of this problem is kind of tricky. So Vi and Vf. The force is the question mark. The time is 0.05 seconds. My mass is 0.105. My initial velocity is 12 meters per second. And my final velocity is actually negative 15 meters per second because that hockey puck completely switched directions and then traveled at 15 meters per second. So now I'm going to plug my numbers in. F times 0.05 equals 0.105. The final velocity is negative 15. The initial velocity is 12. 0.05 F equals negative 2.835. Now to separate the F and the 0.05, I'm going to divide. And the force is negative 56.7 newtons. Now this negative is a directional negative, so you can also say 56.7 newtons in the opposite direction. That just means that the puck is moving to the right and you apply the force to the left. Okay, so in class tomorrow, we're going to actually practice calculating unknown variables using impulse and the change in momentum relationship. So I'll see you tomorrow so we can practice.